From the light you see from a distant star to the sound of your own voice, it's all connected by how energy moves. And it really all comes down to just two fundamental types of waves that pretty much shape our entire reality. So let's get into it.
Let's kick things off with something a little dramatic. Imagine an explosion on the moon. And hey, this isn't just some sci-fi scenario. NASA has actually tracked meteor impacts that create these bright flashes on the lunar surface. In fact, there was one back in 2013 that was so bright you could see it from Earth without a telescope. And that right there, it opens up a really fascinating puzzle. So if you were standing outside on a clear night and saw this happen, you'd see that flash of light. But here's the crazy part. Even if the entire moon just blew up, you wouldn't hear a single thing. It would be a completely silent show. So what's going on here? How can one type of energy from that explosion make the trip all the way to us, but the other one can't? Well, the answer is all about the nature of waves. Okay, so to solve this whole moon mystery, we've got to talk about the universe's #1 energy delivery service, the wave. It doesn't matter if we're talking about sound, light, or even an earthquake. Waves are the main way energy gets from point A to point B.
But here's the really important part. The thing that makes it a wave, it moves energy. But the stuff that's moving through, what scientists call the medium, it doesn't actually travel along with it. The energy zips right through, but the matter itself, it pretty much stays put.
Just picture ripples in a pond, right? A pebble drops and waves spread out, but the water molecules are just bobbing up and down in place. Or think about a stadium wave at a game. People stand up and sit down, but they don't actually run around the stadium. See? In all these cases, the energy is what's traveling, not the people or the water. All right, so this leads us to our first big category of waves. And you could say these waves are a little bit needy. They absolutely positively need something to travel through. We call these mechanical waves, things like sound waves, the seismic waves from an earthquake, or those ripples in the water. They all fit the bill. They work by having particles of a substance literally bump into each other to pass the energy along, and this means they are completely lost in the vacuum of space, and that is a huge clue for our silent moon explosion. So these mechanical waves, they come in two main flavors, and it all depends on how the particles wiggle. In a transverse wave, the particles move up and down, at a right angle to where the energy is headed, kind of like when you shake a rope. In a longitudinal wave, the particles push and pull back and forth in the same direction the energy is traveling.
So take a longitudinal wave, like sound. That back and forth pushing creates these little areas where molecules get all bunched up. We call that compression. And other areas where they're spread out, that's rarefaction. And then for a transverse wave, like on water, that up and down motion gives us those classic peaks or crests and valleys or troughs. Now, when it comes to speed, a mechanical wave is totally dependent on what it's traveling through. Think about it. In a solid, the particles are all packed together, right? So they can pass that energy along super fast. In liquids, they're a bit more spread out, so things slow down. And in gases, where everything's really far apart, well, they're the slowest of all. And that brings us to the other side of the coin. If mechanical waves, like sound, are stuck here on Earth, how in the world does the light from that moon explosion actually reach our eyes? Well, for that, you need a whole different kind of wave. So let's meet the electromagnetic wave, or EM wave for short. Light, radio waves, X-rays, they're all in this club. And unlike their mechanical cousins, they have absolutely no need for matter to travel. They're perfectly happy just cruising through the total emptiness of space. It's the reason we can see stars that are millions of light years away. So, how do they pull this off? It's this incredible dance between electricity and magnetism. A vibrating electric field creates a vibrating magnetic field, and that magnetic field then creates a new electric field, and on it goes. They basically create and recreate each other, building a wave that can just travel forever through nothing. And here's a key detail. All EM waves are transverse. And in a vacuum, every single one of these EM waves travels at the exact same mind-boggling speed. The speed of light. But get this, here's a massive twist. It's the complete opposite of what mechanical waves do. While mechanical waves get faster in denser stuff, EM waves actually slow down when they have to pass through things like air, water, or glass. You know, when we say light, we're really only talking about a tiny slice of this huge thing called the electromagnetic spectrum. It includes everything from the radio waves bringing you music, to the microwaves cooking your food, all the way to the UV rays you get from the sun and the X-rays at the doctor's office. They're all fundamentally the same thing, EM waves. They just have different vibes, different frequencies, and wavelengths. All right, we've met our two main players. One needs a travel buddy, the other is a solo traveler.
One speeds up in solids, the other hits the brakes. It's time for the showdown. Let's put them head to head and see how they stack up.
So let's break it down. The absolute biggest difference, the one you gotta remember, is that mechanical waves need something to travel through. EM waves, they're totally fine in empty space. Then there's the speed. They're polar opposites. Mechanical waves are fastest in solids, while EM waves are fastest in a vacuum. The classic example for a mechanical wave is sound. For an EM wave, it's light. And it all boils down to the physics behind them. One is about particles bumping into each other, the other is about the fundamental forces of electromagnetism.
And look, this isn't just some abstract physics lesson. This stuff has mind-blowing real-world consequences. Back in 2011, there was an earthquake in Virginia, and people started tweeting about the shaking. Now those tweets, they traveled as EM waves. They flew through the internet at nearly the speed of light. And they actually arrived in places like New York before the slow-moving mechanical waves of the earthquake itself got there. How cool is that? They essentially created a makeshift early warning system.
So when you really think about it, these two types of waves are behind almost everything we experience. From the mechanical vibrations your ears pick up as sound, to the electromagnetic waves from the sun that your eyes see as light and feel as heat, they're the universe's primary delivery system for energy.
And that, right there, brings us full circle back to our silent explosion on the moon. We can see it because light is an electromagnetic wave that has no problem crossing the vacuum of space. But we can't hear it because sound is a mechanical wave, and it's got nothing to travel through between here and there. It really makes you think, doesn't it? What other parts of our world are being shaped by this constant, invisible dance of waves? Thanks for joining this Explain.